Okay, so today's speaker is Torres Castillo from BilTop University. So he's going to tell us about quantum non-local games and d-torsion commutative space, or commutative classifying space, I suppose. Okay.
Okay, well, thanks everybody for coming. Uh, well, uh, as usual, we start with some motivation. Um, well, let's suppose we have this game in the sense that uh, I will explain it later. But let's suppose we have over this system, this is a system of linear equations that should satisfy this condition. They should sum 0, 0, 0, 0, 0, 0. Ah, this is 1. Sorry. Okay. 0, 0. Okay. Sorry? Uh, well, well, first, this is think of it just as a system of linear equations. Yes, they should sum 0, 0, 0. Only this column should sum 1. Yes, it's a game in the sense that, oh, it's like an abstraction of this game. I don't know the name, tic-tac-toe or three in a row. Okay, but not exactly. It's an abstraction of, yeah. But non-local in the sense that the players can use a quantum strategy. If we want this linear system to satisfy this condition, well, the problem is that there is no solution in set mode 2. Maybe it also helps to write down what the linear system from. Okay, yeah. X1 plus X2 plus X3 equals 0. X4 plus X5 plus 6. Okay. Well, I will explain this with just this particular one. Okay, let's see. Okay, the mean is X1 plus X4 plus X7 equals 0. This is what I mean. Yes, general. What? So solutions in set mode 2 are referred to as classical solutions. So this is a particular game with no classical solution, but we will see later that there is an operator solution that is like a quantum solution of this game. For convenience, we set like set mode 2 is now -1 and 1, just for notation, and write multiplicatively instead of the additive notation. Yes. Yes, I will explain why this convention. In just a second. Okay, okay, definition. An operator solution. Sorry? SL is any of these rows or columns. Yes. SL? SL is any of the equation. BL is one of these coefficients, 0, 0, 1. It might be more general.
Okay, yeah, this is just a linear equation.
BL is just 0 or 1.
So you're considering like for any sets of BLs, you're considering a game? Yes, yes. A B is just think of it as a column. It's fixed. Here it's 0, 0, 0, 0, 0, 1. Yeah, exactly. And then yes, and then you can construct S as a matrix, and there are like 9 equations and 9 variables. Yeah, okay, that's what I was. It would be better to write it that way, but
Yeah. Yes, this convention is just for the xi's, because for BL we also use the classical notation 0 and 1. Yes. An operator solution of this linear system, okay, a matrix, a vector, is a set of operators x1, xn, in the unitary matrices of order m times m cross m, such that we impose these conditions for all the variables are and the operators are locally compatible. If appear in the same equation. Yes, this is an equation, for instance. Yes, but remember they are not variables but operators. So this is what we say. The operators are locally compatible. Okay, and last condition, we ask for this. Remember, this is a matrix. So A is a matrix, so this is a, well, just a number. Equal minus 1 pi identity. For each I satisfying these equations, these inequalities. Okay. Okay, we will establish the following notation. We will write sol A B um for the set of operator solutions of the linear game or linear system A, comma B. Okay. Another definition, the definition of solution group. The solution group gamma of AB of a linear game A x equals B is the group generated by these variables x1, x, and j that it's like a replacement for -1 in this case, but it's just an abstract replacement satisfying the following relations. Okay, the following relations. J commutes with any of the other variables xi. Xi, xj, xi and xj commute if these variables appear in the same equation the same linear equation. And last one, xi to the xij, j equals j to bi. So that's why I say j is a replacement for -1. Yes.
But you also want to define for arbitrary b, right? Not square because talk about ordering.
Yes. So this is just the standard name for this particular case. But more generally, we are interested in the case where we, instead of using this condition, we ask for this more general condition, D and D. So in this sense, the variables are d-torsion, where D is this 2 or greater than 2. Yes, this is a more general formulation. Yes. Okay, just before stating a proposition, I need to mention a category. The category group J, where the objects are pairs, where G is a group and JG is a. Sorry?
How can 2 be false? Always true.
Yes, this is what we ask for, because J must commute with all the other variables. Yes, this is an abstract generator. It's a generator, yes. Commutes with the other generators. Yeah, it's abstractly -1, but it's not actually -1. Yeah, this. So G is a group. This guy is the G is a central element of order D. Well, okay, we should maybe include the D in the notation, probably. But let's suppose we assume D. We know D. And the morphisms of this category are, well, homomorphism from G to H, such that it sends Gj to Jg to Jh. Yes, we only ask for this condition. Okay. Okay. Uh, it's not direct, but if you can translate the language of linear games to the language of simplicial sets, yes, you can.
Not really, yeah. No, not a good one. Yeah, I mean, you can kind of do. Okay, so the purpose of the paper was to come up with something like that. Turn solutions into morphisms in a category, and then try to understand how to relate it to linear systems. So it turns out you can actually model these things in sets. And I'm not sure if Victor is going to talk about it, but essentially the crucial information about the linear system is this.
Yeah.
Yeah, so that's probably what we will get to. So you can think of it as this group is encoding the linear system.
Exactly. Because.
Yeah, I mean, you can think about group homomorphism. Yeah. These things, but maybe relax it. I don't know. So it's not really. Yeah, I mean, you can define a yeah, that, maybe those groups which preserve the J elements or something. Yeah. That could be. I think you can cook up something like that. Or all. I mean, in the category.
We fix a central element. Yes. D is fixed. Yes.
No, these are just groups with central elements.
No.
So this category is the solutions, right? The group element groups and the central elements in there. There's no matrix A or B in there. But you can see the discrete group defined as finite group as an element of that, as an object of that category.
Yeah, I should include this. Okay. I just said. Okay, I forgot this. Okay, now it's complete. Okay. Remember, A is a matrix M times cross N. Yes. That's why M and N. And okay, so what is the relation or the connection with operator solutions? Well, there is a bijective correspondence between, okay. Well, this set of solutions, operator solutions, can be more generalized defined for a group of this kind. Yes. And there is a bijective correspondence between this two sets. This is a proposition by Chung-Okay and Sikora. Okay, so if we want to, we are only interested in this case, yes, we can replace it by UN. Yes, okay, yes. We have to choose a central element in UN. Yeah. Is a general group with a central element previously chosen. Oh. Yeah. Uh, no. Just to emphasize the connection between both notions. Yes. Okay, but why we are interested in more general cases? I mean, for us, it's enough to study this case, right? Why we are interested in more general groups? Well, there is a reason, and it's given by Slofstra. Did this mention in your paper, Cihan? So you thank to Slofstra for this result. So I should mention this. Okay, if the set of solutions, the operator solution is not empty, the set of solutions for this group, some finite group, is non-empty. Some finite group G. Yes. So if we are interested in operator solutions, we might restrict just to finite groups. Yes. Okay. It's co-limit argument or something like that. Yes.
I can't remember exactly
Yeah. Somehow it uses that any finite group can be embedded in some UM. Yes.
Yeah, I think probably using something about finite integral subgroups of UN.
So from now on, we only have to restrict to finite group. Well, there is a conjecture by Chung-Okay and Sikora that says the following. Now let the larger than 1 be a not integer if the set of solutions in G of this linear game is non-empty. The linear game AB admits a solution in set mod D, i.e. a classical solution. Okay, we remember. We have to choose a group G, a finite group G. Yes. For some G.
For some G that
Let G with a central element group. Yes. Right. Okay. Well, but we remember that the magic square game has no classical solution. When d equals 2, the linear game, well, the magic square game, the graph associated to this game is often denoted K33. It's called magic square game, or maybe Mermin-Peres game. There are 2 or 3 names. So this game admits a solution in this group, the extra special group okay. This is the special group. Also, we can find it as the central product of D8 with D8. But it doesn't admit a classical solution. That's why the conjecture only includes odd integers. Yes. Now, the d-torsion commutative space. Well, let's remember the following simplistic set. Construct a solution. Well, the group is independent of the linear system, in fact. Well, the conjecture says that the binary case is different in nature to the case for another D. Yes. Yeah. Oh, okay. This implicit set goes n simplices are given by well, there is a translation of this conjecture in terms of contextuality, but I should say something about that, but right. Okay. Well, this is the set of n simplices, are the tuples, such that these elements satisfy this condition. They are d-torsion, they are pairwise commutative, for all I, j, satisfying these inequalities. Okay, we remember this simplicity set. Well, I won't define the phase maps and the degeneracy maps, but we might imagine which are. Okay, let this pair be in the category group G, group J. The central extension one, its inclusion, the projection. Okay, remember JG is a central element of d-torsion of order D. So this is isomorphic to set mod D. Okay, so allows to induce vibration and set mod D, the nerve, the d-torsion commutative nerve, and well, the orbit space. I will give some more details. Where M bar set mod DG is the orbit space under this action of NCD on the d-torsion commutative nerve. Okay, let's see. D1 AN, D1 GN, defined by the following: J A1, D1, J AN, GN. Okay, remember that J is central in G. Now, this vibration is classified by a cohomology class. A cohomology class in this second homology group. The class of, well, we can denote it by gamma GD. Okay, so the previous conjecture, this one, amounts to showing that this class vanishes. Well, this is not precisely evident or direct. So this is essentially a proposition by Chung-Okay-Sikora. Okay, so we are trying to show the vanishing of a cohomology class. That's the conjecture, in fact. Now, to make some progress towards the conjecture, we will exploit the homotopy structure of these simplicity sets, particularly this simplicity set M bar, set mod DG is homotopy equivalent to the homotopical limit of these nerves, where A is a group in this poset. I will explain what is this. This guy is just the quotient of A over J. And this poset, or well, this set in principle, is the set of groups that contain J, such that A is abelian, and d-torsion. Okay, so that's why it makes sense, this quotient, because A contains J. Oh, well, in fact, I should try this. Yes, to be more precise. Okay, the general conjecture, uh, it's it's hard so far. So we might restrict to the case D equals a not prime. We henceforth assume that D equals P a not prime. Now, by the Bosfield-Kahn spectral sequence, we have the following. The higher limits, or the cohomology groups of these guys. Now, instead of set mod P, I just write FP because it's a ring. Well, it's a field, in fact. Now, A belongs to this poset J, G. This spectral sequence converges to the cohomology of this implicit set, the quotient. Okay. Okay, it's not hard to check that the following holds, and lim 1 of H1 dj. Therefore, we have exact sequence of this form, lim 1 of H1 A bar H2 N bar Z not P G FP and lim 0 H2 A bar FP. Okay, this is more simplified. Okay. Okay, this homomorphism is injective. Our class gamma GP lives here, and the image of this class here is trivial, is 0. Therefore, because of this, there is a pre-image of this class living here called gamma hat. There is only one. Okay, that is sent to gamma GP by this monomorphism. Okay, so if gamma hat is 0, gamma GP is trivial. So we want to show that, we have to show, in fact, that gamma hat is trivial. But maybe it's natural to ask if lim1 of H1 is 0. So immediately implies that it implies the conjecture. Because of the form of the spectral sequence, yes, they're not differential. Yes. Yes, this is not in my notes so far. Sorry, but yes, check it. Yes. Right. Thanks, everyone. So if lim1 H1 is 0, then the conjecture holds for G J. Okay, so at some point we expected to show that maybe lim1, this higher limit, is always trivial, but it won't be the case, in fact. Oh, a small observation before continue. An element in this pole set is elementary abelian. Because of its p-torsion. It's abelian and p-torsion, it's elementary abelian. Oh, well, for who are not familiar with this, A is isomorphic to Z mod P to the N for some N. Okay. This includes the group generated by J that is isomorphic to Z mod P by assumption. Now, the higher limits can be computed as the cohomology groups of R certain cochain complex. Is the first cohomology group of this cochain complex. Sometimes I will omit to write the poset if there is no problem, just to avoid overcharging the notation. Where this is the cochain complex. The cochain complex is given by these products, H1 of A bar, Fp, and this string of arrows but we can take normalized chains, so we can assume that they are not equalities. So they are strict inclusions. A bar of n. A bar sub n. This. And well, we can instead write this by one, a n bar dual, because of this is the first cohomology group. A 0, a n. Okay. Okay. Well, there are some differentials that I guess we don't need to define. Is everybody here familiar with higher limits? So I guess so. A small observation. I won't define the differentials because of the time, but this is immediate from this situation. If n is greater or equal than the p rank of G minus 1, then the cochain model is trivial. So corollary, the conjecture holds P rank 2 groups. For example, the metacyclic other groups, etc. And this includes this, for instance, this is the special group by 1 plus 2. Okay. Let's give an example. Let's take this example, the grid product of Z mod 3 with Z mod 3. This is the poset. Z mod 3 square not 3. Okay. This this group is of P rank 3, but there are 3 copies of set. Well, no problem. There are 3 copies that are conjugated. Like here, there is only 1 copy, 3 copies, and they are all are subgroups of the single copy of C3 to the cube. Yes. So, and in this particular case, the P rank of this group is 3. But we can take the poset of maximal subgroups, and this simplifies the poset. Okay, which are the maximal objects? The maximal subgroups are this one and this one. So we can simplify this. Now, I will say this, a poset of maximal subgroups. Now it's easy to see that the first Cochet model for this poset is 0. So lim1 of this poset is trivial, because we can replace the poset for this simpler one, and it doesn't change the value of the higher limit. Okay, so this is an example of P rank 3 group. Okay, the P rank 3 case. This is the next step. Okay, let's suppose that the P rank 3 of G is 3. Then we have this exact sequence. I will simplify the notation here. Lim0 of H1, I won't write this. Is 0, C1, lim1, 0. Okay. Because there is no C2 in this case. C2 equals 0. Well, this is lim0 of H1, lim1 of H1. Okay, I won't write it here anymore. But they all are FP models or FP vector spaces. So we can write this. This guy is a power of FP and 1 of G. So I will do the same here. N2G FP to the N3G. And last one, FP to the N4G. We want to show that N4 of G is trivial, is 0. Well, we have the following. We can show by, again, the Bose-Filkan spectral sequence that H1 of G is the P rank of the fundamental group of this implicit set, the quotient. Sorry, the abelianization of this guy. Again, just by Bose-Filkan spectral sequence, lim 0 is isomorphic to H1 m bar Z mod P G FP. So we obtain Bose-Filkan spectral sequence. Okay. Okay. N2 of G is the number of copies of Z mod P square in the poset plus 2 times the number of copies of CP cube in the poset, and N3G the number of inclusions from Z mod P square to Z mod P cube. Okay. This is just by the definition of this cochain complex. Okay, by Euler characteristic, link 1 vanishes if and only if n1 of G equals n2 of G minus n3 of G. Okay, this is like a reduction of the problem. This is the most complicated invariant, let's say. But GAP can compute this invariant for many groups. So we can make a code to define this invariant, and GAP can compute N1 of G. Okay, a small observation. To simplify the notation, we will say that this is our poset. APG is denoted by cursive P. Okay. Remember that our functor is an invariant functor that sends A to H1 of A bar F P. Okay, so we will follow this convention, let's say. Now, since f of the group generated by J is trivial, we don't have to consider the first level of the poset. We only need to consider the interval, the poset of objects that strictly contains J. Ah, oh, okay, because C0 is defined as well, product of f of an, right? So, okay, an. But let's suppose that AN is a copy of CP cube. F of AN is CP square. Right? Right. A1 is CP. Right. Yes. Okay, so we only have to consider this poset that simplifies a lot the problem. And on the other side, the poset of object that externally contains J is has height 1. Okay, it's height 1. So it's uh, it's a wedge of spheres, a wedge of circles. Now we will be interested in the case where this poset or this interval is contractible. Uh, then the Euler characteristic of this poset, well, is 1. But at the same time, this is the number of copies of set mod p squared plus the number of set p cubed minus the number of arrows inclusions. So that is 1. Okay. Thus, under this assumption, that this poset is contractible, lim 1 is 0 if and only if n1 of G equals the number of copies of set mod p cubed plus 1. Yes. So if we make a code for gap, we only have to check this condition. Of course, we have to assume this situation. This poset is contractible. The good news is that this poset is many times contractible. So, okay, for simplicity, we will assume that we will restrict to this case. The case that G is a P group, a finite P group. Now the question is, when this poset is contractible? Well, there are some results about this poset, or well, a poset closely related to our poset. A theorem by Brook and Tebnas says the following. This open interval has the homotopy type of a wedge of spheres but possibly of different dimension. Yes. Of possibly different dimensions. We still have time. Oh, yeah, fine. Example. Well, this theorem includes the case P equals 2. Okay? For example, let's suppose that we have this group, the identity of this group, the ID of this group in GAP is 64 to 158. So dispose it for a chosen J is homotopy equivalent to 2 copies of S0 and 4 copies of the circle. Yes, this is an example given by book. So at least in the case P equals 2, we know that the dimensions can differ. Yes, oh, the dimension of the spheres. So lemma, if the center of the group P is not cyclic, is non-cyclic, this poset is contractible. Yes, a small proof. We can use the Quillen fiber lemma. Just take set and we will have that the poset is conically contractible. Okay. Yes. Yes, because there is an equivalence with this poset. Yes. Exactly. Yes. Oh, well, an example where lim1 is non-trivial, it's important, of course. I will give one. An example, lim1 is non-trivial. But the simplest case, remember this criterion also includes the case P equals 2. The conjecture doesn't, but this criterion also includes this case. Let's take this example. The central product, that is the extra special group of order 34, 32. The P rank of this group is 3, of course. And we know that this is the center. We can take J as the generator of the center. Okay. In this poset are 9 copies of Z mod 2 square, 6 copies of Z mod 2 to the cube, and 18 inclusions, arrows. Z2 square, Z mod 2 to the cube. Because for each copy of Z mod 2 to the square, there are two arrows, yes. For each copy of Z mod 2 square, yes.
I think it would be nice to connect the poset to the first thing you showed, magic square.
It should be fine, yeah. In fact, this is the example given by the Mermin-Peres square game.
They're the same thing, essentially. Because you talked about the graph, but I think you can tell what the conversion is. Linear systematic graph, but they encode the same thing, the poset, the graph, and the thing.
Exactly. N1, well, we know N1 because pi 1 of N Z mod 2 G, in this case, is Z mod 2 to the 4. So N1 is 4. N2 of G is 9 plus 2 times 6, that is 21. And N3G equals 18. So N4, so the dimension of link 1 is 1. Link 1 is non-trivial. Well, there is an example for p equals 3. Example for p equals 3. We have to take this extra special group that is analogous to this case, and also link 1 is non-trivial.
1 plus 4?
Plus 4, sorry. Yes.
For this example, you're not using this.
No, the center is cyclic in this case. That's why they don't satisfy this condition.
So this
For contractible cases. We use the contractible case to reduce to this situation.
your example is not
I don't know, they were the only examples where lim 1 is non-trivial. Yes, because the conjecture is that if, well, the conjecture is that si center is non-cyclic, lim 1 is 0. The final result, let's say. Yes, sorry, non-cyclic example, yes. That's why, yeah, as you said. Where are you? Okay. Oh, okay. Yeah. It's only an example where link 1 is non-trivial. Yes, sorry for that. I should have given the example before this resolved by Tebnas. To find this? Well, this is resolved by a paper of Cihan, and yes.
So this contractible case
Exactly. Yes, the criterion, yes. Those candidates to have lim 1 non-trivial are those that have disposed non-contractible. Yeah. Yeah. The same idea, yes. Yes, for this case. Yeah, for many cases, it's accessible for computation. Yes. Ah, yeah. Sorry, I missed it. There are connections. Yes. Oh. Oh, fine. Yeah, I will have a look. Great. Yes. Okay. Sorry. And what if the center is cyclic? Okay. So there is a result, a strong result by Fumagalli and Sharesha. I will just mention a consequence of their theorem that says the following. If P doesn't contain a subgroup isomorphic to the extra special of this extra special, then this poset is contractible. It's a consequence of the theorem. No, no, it's not an infinite. Yes, it's a particular situation. Yes. Right. Okay. So we only have to take care of these cases. Those groups that contain well, not exactly, but they are those groups that contains these extra special groups are the pathological ones, let's say. So well, we have a conjecture or a pre-theorem. Not all the details are given yet, but we made some progress towards the following result. Let P be a P group of P rank 3. Then if either the center is non-cyclic or well, the center is cyclic and P doesn't contain a group isomorphic to this extra special, but there is no problem with this group. Okay, there we can include this possibility because of this group is P rank 2. The only problematic one is starting from this case. Well, there are some details to refine, but let's say I will just give the idea. We are under this assumption, yes. P rank is 3. Right. Sorry. This way. This is the only situation that we have to avoid, yes. It contains this. The conclusion is that, well, remember, it's still a conjecture. There's some details to clarify. But if P doesn't contain this extra special group, link 1 is 0. Link 1 is 0, yes. So remember, just the idea. The height of this poset is 1. So let's suppose this situation. Suppose that we have 4 copies of Z mod P square and some copies of Z mod P cube. Okay. Just to give an example of the idea. There is another color. Okay. We have the subposet that those that are containing x1, those that contain x2, x3, and x4. And look at the intersections. Are just, they can only be points. There is no other possibility. So for simplicity, let's suppose that the poset is contractible because if the poset contains a copy of this, it's not contractible, but it's contractible plus some isolated points. So let's assume this case. Okay, let's suppose that this is the poset. This poset is denoted by this, etc. So here is the thing. Link 1 restricted to these posets is 0. So we have to exploit this fact. That this poset intersection with the next one is just a point. There is no other possibility. And start with this case. Let's suppose that our poset is a union of 2 of these guys. Then proceed by induction. So let's say the idea is to apply Mayer-Vietoris, but we have to be careful about this because it's not immediately true. Let's say we have like a Mayer-Vietoris exact sequence. Let's start with this case. Let's denote this by P, X, Y. We have almost ready. Okay, we have that these guys are trivial, 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 trivial. So this is the only part of the sequence we have to work on. But some details are still to clarify. But yes, this is the strategy and the idea of the proof for this conjecture. Yeah, that's why I have to be careful, because at least in the P rank 3 case, instead of link 1 of H homology, first homology, we can take column 1 of first homology, because they are isomorphic. Yes. So we cannot, Meyer-Beatrice sequence doesn't apply to this case, but it does apply to this higher colimit. So yeah, we have to be careful. This is not enough to finish the proof, but it's a progress. Yeah. So, and well, as I said, if P contains this extra special group, it's essentially the same, only with some isolated points, but they don't change the link one. Well, that's all for today.
Okay, thank you.
Okay.
Any questions for Victor? So you are assuming CP is not cyclic, which means
Contractible.
the will be contractible.
Positive contractible.
No other input,
Well, uh, I only need the fact to, well, I need the fact that the poset has some geometry, let's say. Yes, I only need to use that this is contractible, and each of these subposets intersect just in one point. Yes. But yeah, because in this case, link one won't be trivial. 1 + 2, yes. I don't have, well, this is the case where I have to be careful, but my first computations were that if there is a copy of this special group, the poset is like this, plus some copies of Z mod P square, isolated, and they don't change the lim one. They don't change the variant. Yes. Yes, this will be the next step, because apparently by this proposition, yes, we might train this strategy for higher P ranks. But I'm not sure about. Uh, Not exactly, because we have to. Oh well, we would like to answer the conjecture for those groups that contains this extra special group. But in the paper by Cihan and Igor, they show that the conjecture holds for this group. Now the question is just for groups that contains the. Doesn't contain, yes, because yes. Well, the treatment for this case, yes, will be different because we don't expect anything from this criterion for this case. Yes, because for instance, for link one, for exactly this group, the dimension of this guy is, well, link one in fact is F3 to the 44, so it's completely non-trivial. Yes. Limit non-zero, limit non-zero. So we know that the conjecture, the class vanishes for this group, but for another method, let's say, other arguments. But the class is zero, yes.
Yeah, I think the expectation is contain special. Yeah, maybe in general that's
This is not problematic because essentially because of this group is P rank 2. Link 1 0, yes. The conjecture holds. Yes. Right, yes. Yeah. Yeah. Thanks for your question.
Thank you.
Thank you.